Alkaline waste dump alters seafloor ecosystem near LA. A recently published study sheds new light on the environmental legacy of industrial waste disposal practices off California's coast, specifically in the San Pedro Basin, where tens of thousands of corroding steel barrels have been sitting on the seafloor for decades. Originally believed to contain mostly DDT-tainted materials, researchers now estimate that nearly one-third of these barrels instead held alkaline industrial waste legally disposed of in the 1960s. Between 1961 and 1964, the Pacific Ocean Disposal Company released approximately 1.38 million gallons of highly caustic alkaline waste into the basin. As the steel containers have deteriorated over time, the leaked substances have triggered notable chemical interactions with seafloor sediments. The reaction between the waste and sediment pore water magnesium has formed brucite-rich mineral zones, creating 1-meter-wide formations around each affected barrel. These reactions have produced striking white calcium carbonate halos, distinctive mineral precipitates that now serve as visual indicators for identifying barrels that originally contained alkaline waste. The process closely resembles serpentinization seen at natural hydrothermal vent systems, where highly alkaline environments support unique chemical and biological activity. The new visual markers are proving useful for survey teams, providing a faster way to distinguish between different types of waste containers during remote underwater assessments. Specialized microbial life emerges in alkaline seafloor zones. Beyond mineral changes, the dumped alkaline waste has triggered a significant biological shift in local marine microbiology. Sediment core samples from these areas show microbial communities that are less diverse but heavily adapted to extreme pH conditions, some as high as pH 12. These altered zones are now dominated by alkalophilic bacterial species similar to those found in deep subsurface aquifers and hyperalkaline springs. Genomic sequencing of the microbial DNA indicates these species rely on mechanisms such as sodium-driven ATP synthases and multiple sodium-hydrogen antiporters to regulate internal pH and maintain cellular processes. These adaptations highlight how rapidly ecosystems can reorganize in response to chemical disruption. However, this shift toward extremophile life forms comes with ecological trade-offs. Affected zones support significantly lower overall microbial abundance and limited functional diversity, raising concerns about long-term disruption to natural biogeochemical processes on the seafloor. Since brucite dissolves slowly in seawater, the researchers suggest these chemically altered zones could persist for thousands of years.